Okay, it's recording now. So thank you for coming. So today tutorial, we're going to do revision 1 on Boolean Algebra, revision 2 on sum of product and product of sum. Then we go through the tutorial 2 and we can have the Q&A session after that. Let's get started. So the Boolean Algebra developed by George Boolean, 1854. Basic knowledge of the Boolean algebra. When you say Boolean, the answer is 0 or 1, true or false. The input, there can be one or multiple input. It can be 0 or 1, each of the input. That's why you call it a Boolean algebra. Okay, each variable can only have two values, 0 or 1. That's the meaning of Boolean. A variable is a symbol to represent a logical quantity. It can either have 0 or 1 value. A complement or inverse of variable indicated by a bar or a prime number. Literal is a variable or its complement. Okay, so you have three laws: commutative law, associative law, and distributive law. Okay, this one you learn also in basic maths. So commutative law, A plus B equals to B plus A. A times B equals to B times A. Okay. So this is only applicable for addition and multiplication. Okay. It might not applicable for other operation. Only addition and multiplication. Then you have associative law, A plus bracket B plus C equals to bracket A plus B, close bracket, plus C. Then it's also the same thing for multiplication. And also you have distributive law. Okay. So then we see there's 12 rules in Boolean algebra. So when you say plus, what does it mean? It means a OR gate. When you say dot, it means a AND gate. Okay. Are you all clear? Yeah. Okay. So let's start it all over again so that it's more fluent. Okay. A plus 0. What is plus? Plus is an OR gate, isn't it? A or 0 will become A. All right. A plus 1 equals to A or 1, so it's 1. A times 0 equals to A and 0, so it will be 0. A times 1 equals to A and 1, so equals to A. A plus A equals to A, okay? A plus A bar. A bar we put like this. Equals to 1. How do you prove it? Okay, let's A equals to 1. Okay, so A bar equals to what? A bar will be equal to 0. So A plus, okay? Oops. Let's A equals to 1 and A bar. So what is A plus A bar? Equals to 1 plus 0. 1 or 0 equals to 1. All right, so let's go another one. Okay, so what is A times A equals to A lah. Okay. A times A bar, right, equals to, okay, let's say, let's A equals to 0. So A bar will be equals to 1. So A times A bar prime equals to 1. 0 times 1 equals to 0. Okay, you can also let A equals to 1. A prime will be equals to 0. So A times A bar equals to 1 times 0 equals to 0. Okay. Right, then the next one. This one. This one, A bar bar. Okay. So let A equals to 0. So what is A bar will be equals to 1, eh? So A bar bracket bar will be equals to 1 bar, which is equals to 0, which is equals to A. Alright, you can also do let A equals to 1. So A bar equals to 0. So A bar equals to 0 bar. Equals to 1 equals to A. Okay, so this proves everything. Okay, right, so another one, you try writing here. Rule number 10, A plus AB will be equivalent to, let's see, let's try here lah. The small space we have, the very little space we have. Very little space we have. So A plus AB equals to A1 plus B, which is equals to A. Because 1 plus B is equals to A, equals to 1, okay? So then A plus A bar B equals to A1 plus AB plus A prime B. So this one will be equivalent to A plus A B B, then you have A plus A bar. Then A plus B bracket will be A plus C is equal to A plus, oh what? Plus BA plus AC plus BA plus AC plus BC. So this is equal to A1 plus B plus C plus BC equals to A plus BC. Okay, so in this case, rule 1 to 9 is self-explanatory. Rule 10 to 12, you must remember in order for you to do the simplification. Okay, any question so far? So far, any question? Any question? Clear? Clear? Okay. No question now. Okay. Yeah, so far so good. Okay, so the next thing is these are the simply rule in circuit term, all right, which is self-explanatory. Basically, in this rule 10 to 12, you can also prove by using the truth table. But using truth table may be longer lah. Because you need to consider every steps. Okay. Right. Okay, so this also you can prove by truth table. Okay, the next thing is De Morgan's law. This Morgan's law is x times y bar equals to x bar plus y bar. and x plus y bar is equal to x bar times y bar. So these are the two rules. So when you implement it in circuit, it also means like this. NAND gate is equal to negative NOR gates, and then NOR gate equals to negative AND gates. All right, negative AND gates. All right, later we can show it to you. So this circle is actually an inverter. Okay, both of them, you do the truth table, you can get the same answer. And this is how you do circuit simplification. Okay, circuit simplification. Okay, clear? Then we look at the problem. Okay, problem 1. So here you have AB, and then here you have CD. So X will become AB plus C plus D. All right. So this is self-explanatory. Then you have this one, A. So you have AB over here, then you have CD. So this one will be ABCD. Okay. Then you have this one. So first you have AB over here. Then you have CD. Then you have ABCD. Then you have A bar here. So over here will be X will be equal to ABCD plus A bar. Okay. And then you can further simplify it to become all right, to become X equals to X bar plus BCD, because this one you follow rule 11, I think. Okay, rule 11. Rule 11 of previously one. Previous one, Boolean Algebra, rule 11, this one. Okay. Okay. Then you have problem number 3. Okay, example 4, you also have this one. So this AB, then you have BC, then you have B bar here, and then you have A plus B bar. Then you get the answer. The answer will be X will be equal to AB plus B bar times BC. So this one is equal to ABC plus B bar times B times C. So B bar times B is always 0. Anything times 0 is 0. So you get back ABCD. All right. Then example number 5. All right. So here you have A prime, you have AB here, you have B prime here, and you have C plus D here. Then this one will be A bar plus AB. This one will be B bar times C plus D. And when you add up together, you get this one. So from this one, you need to simplify. So from here, you use the rule 11. So you get A bar plus B. And you rearrange it. All right, you put it inside. Okay, then from here, you use rule 11. Rule 11, okay, A prime plus B, A bar plus AB equals to A bar plus B. All right. Then from this one and this one, B and BD, you use rule 11, you get back equals to A plus B plus C and D. Okay. Okay. Over here you see B plus BD equals to B plus D. Okay. So this is how you simplify. Okay. So you can see the two circuits are different, but the output is the same. So what you can say is that these two circuit is a equivalent circuit. It's an equivalent circuit. Okay, the circuit is a equivalent. Then you also have problem D. So this one is using De Morgan's theorem. So basically is A. So you have A plus B bar. Then you have CD. Then over here you have what you call that? X equals to this one. So first you use De Morgan's theorem. You take out the big bar, become a small bar. Okay. So this one will become this one. Okay. And this part. Okay. I cannot break this out because of the what? Then from here, it become this one. Okay. This bar CD will become CD. So this one bar A plus B will become A plus B. So you have this one. Okay. All right. So you can also okay. So we will back to example 6. Example 6. Okay. Okay. Example 6. Let me draw it. Okay. Example 6. We're going to do back example 6 later on. Okay. So you can also do simplification using the Boolean algebra. So over here, okay, they're already done in the formula form. It's difficult for me to edit, but you can see here, first B plus B. So this one, you remove the B bar here. You use a rule 11. You get here, this one. Then you bring it in, you rearrange, you get ACD plus B times A bar plus ABCD. Okay. Then you take out the B, you have A bar plus ACD prime. Okay. So you remove the A from CD. Okay. Then you get the simplified solution. All right. So basically all this problem 2 to problem 4, okay, you use De Morgan's theorem. You use rule 10, 11, 12, and De Morgan's rules to simplify the circuit, okay, the expression. Okay, so far any question? So far any question? Any question so far? Feeling confused? What is confused? What is confusing? Rule 10, okay, rule 10. Rule 10 is what? Also cannot remember the rules, okay? A plus AB equals to A. All right, so how do you prove it? A plus AB equals to A, 1 plus B, right? Equals to 1, equals to A. Thus proven. Okay?
Sir.
Yes, rule 11, is it?
Yeah, rule
Rule
11.
11. Okay, rule 11. Okay. Rule 11 is, okay, let's look at the chat box. There are plenty of things. So A plus A prime B equals to A plus B, is it? Correct? So so this one, A plus A prime B equals to A, 1 plus AB, okay, 1 plus B plus A prime B. So equals to A plus AB plus A equals to A plus 1 B A plus A prime equals to A plus B. Okay, so let A equals to Z prime. Okay, so Z prime plus ZB equals to Z plus B. Plus Z prime plus Z prime plus ZB equals to Z prime plus B. Okay? Yeah.
Sir,
Yes.
this one, the A plus A prime B is equal to A1 plus B plus A prime B.
So this one is this how you simplify, ma? If not, how do you prove it?
So I
What
have
is
to,
1 plus B? 1 plus B is what? Is equals to 1.
okay, but
So there's a jump in the thinking, lah. So
from rule number 2, is it?
yeah.
Makes sense.
Okay. Okay, so the thing is that you must be very creative, all right? And you must know how. Yeah.
Yeah,
In
I think
Cantonese, you say "jin wan mo kok." I don't know how you say in English. You twist and turn. You must know how to twist and turn the idea. Okay.
well,
Think out of the box.
but that's gonna be hard to to figure out what kind of
You
idea
are
would
live
be.
in the new age. All right. In the new age. All right. Of creativity. So you just see lah all the YouTube video. You know. You think of something that is so simple that you cannot think of like this. Okay? Okay, so okay, that's about the end. So I'm going to show you how this Demorgan's rule is going to use in circuit simplification. So let me open the slide. Where's the Demorgan's rule? Okay, you just remember this. NAND gate is equal to negative OR and NOR gate is equal to negative N. And we're going to use the, what you call that? We're going to use the circuit as an example. So we say that NAND, just remember this, NAND equals to negative OR and also NOR equals to negative NAND. Okay? Okay, and we're going to use example 6. So this example 6, where's example 6? Okay, we're going to use example 6. Okay, so CD prime and this A plus B prime. Okay, so let's stop the sharing and then we go to the circuit was circuit was go simulator. Okay, so let's do some input. There's 2 input here. Okay, another input. Okay, wait, I'm going to share the file window. Okay, share it. Okay, so then put another input here. Another input here. Okay, so the gates. So first you have a NOR gate here. Then you have a NAND gate. Okay. Then over here, then you have also a NAND gate over here. Okay. Then you connect. And then the output is here. This example 6. So let's do the notation. So this is A, this is B, this is B, and this is D. Okay. Right. So this is example 6. Example 6. Yeah. Let's put example 6. Okay. So we are saying that what you call that? N is equals to negative. Okay, and no is equals to negative n. Okay, so we're going to change this circuit. So we're going to say n is equals to negative. N is equals to negative all, isn't it? So we're going to change this one. We're going to change this one. Oh yeah. We're going to change this one to become this one. So it will look like this. I have to draw everything all over again. Can we cut and paste? Cannot. Okay, never mind. We draw again. So we draw again. Have to draw fast. Hey. We did. Okay. So then we take the gates. So this okay, and this one. Then we connect it. Oops. Okay. Okay. Then from here, we put in a OR gate. But then it say NAND equals to negative OR, isn't it? So there's no negative OR gate, so we put an inverter here. Okay, so connect. Okay, and the output is here. So okay, so let you put it, change here 1, I become 1. It's the same. Okay, so when you put 0 here, when everything is 0, so this one is the same as this one. Okay, but then if you look properly, this is one inverter, this is one inverter, correct? This is one inverter, this is one inverter, correct? So actually, what you can do is that you can actually come like this. And you connect. This one we need longer wait so that, okay. Okay, and these two circuit is the same. Can you see that? So this is how you use this to simplify the gates. Okay, and let's say you have a circuit like this. You can use this way to simplify so that you can make the circuit to become N and O. Okay, N and O. Okay, so you make this so that you can use this method, De Morgan's theorem, to simplify the circuit so that you can use the circuit, and that circuit will use this circuit will use this this is the method used to design circuit using only mains or no. Right? So these are the method they use. Okay. Any questions so far? So I need to save it. How do I save it? Must log in. How do I save it? Okay, never mind. Don't need to save. Okay, so far, any question? Any question? Any question? Any question? No, Okay, so this is how you use De Morgan's theorem. Okay, so if you look at the example 6, you can find out that from here, what is that? The formula x is equal to what? A plus B plus CD. So this is A, this is B, this is B, and this is C. Right? So the answer is this one, isn't it? X. Okay. So generally we finish the lecture 1 revision. So now we go to lecture 2. Okay. So I stop sharing for a while. Any questions so far? So far so good, Okay. Stop sharing. Okay. The next thing is lecture 2, Safe lah. Okay. So we're going to talk about, how come the PowerPoint is not there? Okay, share. So can you see the PowerPoint slide? Can or not? Okay, so we talk about SOP and POS. So what is the word sum? Sum means what? In English word sum, the meaning of sum. English of sum means what? Sum means what? Means summation, means addition. Sum means this one. Okay, so what gate is it? What gate is it? What gate is it? What gate do you all use for sum? NO, XO. What gate is it? What gate? OR gate. Okay, so product means what? In English term, product, what does product means? AND gate lah. Product means kali lah. Means kali lah. Means multiply. Means AND gate. Okay. Right. So when you say sum of product, what does it mean? When you say sum of product, what does it mean? So it means that you will multiply everything first, then add them up together. Okay. When you say product of sum, you add all variables together, then only you multiply. Okay, right? So that is sum of product and product of sum. Okay, so this is the English definition for it. Okay, so let's look at sum of product. So sum of product, you can only have like this, A bar or B bar. You cannot have in sum of product, you cannot have A, B bar. This one you cannot have double A. Okay, or maybe A, B, C, D. This one cannot. Okay, sum of product. Okay, so you see multiply first, then only you add the multiplication together. Okay. So these are the, okay, so this one you cannot have, you can have A bar, B, and C bar, but you cannot have like this. Okay, you cannot have bar for more than two variables. That is sum of product. Okay, so this example first, you can see first you go through all the AND gates. Okay, then you add them up together. Okay, so let's do a okay. So I stopped sharing for a while. I'm going to show you the circuit simplification process. I'm going to share the MS Word. Okay, so this is the circuit you have just now, isn't it? So then let's have this one. So we're going to put in two inverter. Oops. I'm going to put in two inverter. Okay, it's the same, isn't it? This one negative, negative is positive, isn't it? Then we're going to put in here. Okay, so you have a NAND gate already, correct? So you are using a NAND gate. From a AND gate become a NAND gate. Then from here, okay, what is this? You remember the terms? What you call that? Negative NOR equals to NAND, isn't it? Right? So then you can change this to become a NAND gate. And change it become a NAND gate because this is a negative NOR gate, eh? Negative OR gate. Correct? So you have already successfully changed it to NAND gates only. Okay, clear? Clear? Clear lah? Everyone clear? Clear how you do the simplification using NAND gates. Okay? Clear? This is applying the, you just applying the De theorem. Okay? So now we get back to the PowerPoint slide. Okay. All right. So can you all see the PowerPoint slide now? Can? Okay. So let's say you have a sum of product in this truth table. The output is this one. So you can see 0, 1, 1 is A bar B plus times B times C. 1, 0, 0 is A times B bar times C bar. Okay, then you draw the circuit. So this the circuit looks like. So this is sum of product. Okay, sum of product. So the sum of product is also sometimes you call it the mean term. Mean term means that all the variable must be there like this. Okay, all the 4 variable must be there. So then mean term means that it means a specific scenario in the truth table, right? So like this, the mean term of A bar B C is only one states, one of the possible out of 8 states, right? Okay, so that's the mean term. You only specify one possible state. Okay. So it's like this. So in this case, x equals to A bar BC plus A times B bar C bar. All right. Then the product of sum looks like this. Okay. So in product of sum, so this is how it looks like. So you have product first, then you put it in the AND gate. Okay. You put it in the AND gate at the end. Okay. So you put let's say if you add here, Okay. Then this one will become a negative NOR gate. So what is so you have negative N is what? Oh. Negative N is what? Equals to NOR gate. So you already change the circuit to using NOR gates only. Okay. See that? See that? Okay, you put in all the circle here. So this is product of sum. Okay. So let me remove all the circle so that you maybe another slide. Okay. This slide I remove all this. Only this side I put okay. Okay. So this is a product of sum. Okay. So in product of sum, okay, it looks like this. Okay. So you add up together, then you multiply them. Okay. So conversion, you should be able to convert anything to anything. From SOP to truth table, from SOP to POS, from POS to truth table, from POS to SOP, then from truth table to SOP, from truth table to POS. Okay. So the step to convert SOP to truth table lists all the possible combination of variable in the expression. Convert the expression to a standard form, then place one output for each binary. Okay. So first, you have this A bar B, this one. Okay. So you put this one. X is equals to A bar this one. Okay. So you draw the truth table. A bar, B bar, C. So the output is 1. Then A, B bar, C bar, this one. So this is how you convert the SOP to truth table. Okay. Let's say you have a truth table. You can convert this truth table to SOP. Okay. Or you have the SOP. You can convert this to a truth table. Okay. Any questions so far? Any questions so far? No, Okay. Then you can also convert SOP to POS. So this is the SOP form, eh? So this is 1. So POS, in POS, you see the term 0, 1. The term 0, then you get the sum term. Okay. So in SOP, let's say 0, 0, 1. So it's A bar, B bar, C bar. Okay. All right. So this is SOP. So F is equals to A bar, B bar, C plus A, B bar, C bar plus A, B, C. Okay. So this scenario means that this is not F. This is X. So we say that X is equals to 1 when it's 0, 0, 1, 1, 0, 0, and 1, 1. So this is SOP. Okay. SOP. So in POS, first you have to look for the output equals to 0. Okay. First you have to look for the output is equals to 0. Okay, the output must be 0. So these are the output you look for. Okay, these are all the output that you're going to look for. Okay, clear? Okay. So and first the output must be 0. Okay, must be 0. X must be 0. So then when x equals to 0, then you see lah. If a equals to 0, you use a. If a equals to 1, you use a bar. You can see when a equals to 1, you use a bar. Right? When ABC equals to 0, you use ABC. Okay. When a equals to 0, you use a. When b equals to 1, you use b bar. When c equals to 0, you use c. Okay? All right? Okay, clear. So that is the rules. Okay, now we do the checking. We do the checking. So when x will become 0, when x will become 0, when either one of the, when either all this sum term is 0, isn't it? So you have x equals to a plus b plus c, a plus b, c, a plus b, b, and you have a plus b plus c, then you have a plus b bar plus c. Okay. When x is going to 0, when either one of these become 0. Okay? Okay, let's do the checking. Let's say when a equals to 0, b equals to 0, c equals to 0. So what will happen? X will become 0, ABC 0, eh? Then you times anything, so it's 0 lah. Okay. Let's say when a equals to 0, b equals to 0, c equals to 1. Okay, so let's check. X equals to what? 0 plus 0 plus 1. Then here is what? 0 plus 1 plus 1. And here is 0 plus 1 plus 0. Then here is 1 plus 0 plus 0. Then here is 1 plus 0 plus 1 plus 0. So is equals to 1. Okay? So when x equals to 1, okay, this one, when x equals to 1, what happened? All the sum must be 1. Must, oh, something wrong again. Okay, clear. So that completes the checking. Let's complete the checking. Anything you want to ask? So the first thing you must remember, you must check the output equals to 0. Okay. Then if you see A is equals to 0, you use A. If you see A equals to 1, you use A bar. Okay? All right? Okay, so this is SOP. This is POS. Okay? Any question?
Sir. So the S. So if you say again the A equals 0, B equal SOP at POS.
Which one you want to ask? SOP or POS?
Um, the SOP. You say the
SOP. SOP is this one. SOP is this one. SOP, in SOP, you see x is equal to 1. Okay?
Oh, okay.
For x equals to 1. Okay? In POS, the output must be 0. X must be 0. Okay? In SOP, you look for 1. Okay, so this. Okay? Okay?
Okay.
Yeah? You need to practice now. Okay? Then let's see what's up. So these are some of the exercises. Converse. Okay. Then you can also convert from POS to SOP. Okay. So these are some of the exercises. So if you can see here. Okay. So okay, the final term will be F is X, not F. It's X, not F. Okay. All right. This is how you convert from truth table to SOP. So you need to do practice. Practice. So from the truth table to SOP, then you can do the equivalent circuit. Okay, these are equivalent gates. Okay, this is the equivalent OR gates. Karnaugh map we'll do in another tutorial. Okay, any questions so far? So you must do the practice. The only thing is practice. Practice from SOP, POS, and to truth table. So meaning that I can give you SOP, then I say I want the POS, or I want the truth table. Or I can give you the truth table, and you give me the POS. Okay, I can also say I got SOP, give me POS. Okay. Anyway, you must be able to do it in any way and any form. Okay. Okay. So now let's go to the tutorial. So this part we have finished the lecture 2. Tutorial theme. Lab 2. Okay. Okay. So this is the lab that you're supposed to do. Okay. So you have studied the truth table. Can you see the PDF? Can you see the PDF? Can or cannot? Okay, can you see the PDF? Yes, huh? Okay. So perform the truth table and the logic gate using the IC. Okay. So in your circuit words, you don't have IC. So okay, now what you're supposed to do is that you open this PDF file for your reference in your PC. Then what I shall do is that I shall open a simulator. Okay? And you see the simulator. Okay. Right. So the question asks, study the truth table of the logic gate. All right. Okay. NAND gate, NAND, NOR, and OR. Okay. So I'm going to stop sharing for a while. This one, I'm going to, and I'll try to present. Oh, so what I'm going to do is that okay, this is the attendance. Okay, you can take your attendance now. I'm going to present my entire screen. Okay. Share entire screen. So you can see the entire screen. So can you see the digital works or not? Can you see the digital works? Okay. All right. So file, open. There is it. Don't have it. Okay. X. So D X. There's X. Okay. All right. Can you all see this? So this is a logic diagram. So the logic diagram, this is an AND gate, isn't it? So like this. So you can change the input, or first you have to run it. Okay. So this logic diagram. Okay. Then you can use the circuit diagram. So in the circuit diagram, you have to refer to your PDF file, isn't it? So a PDF file 7400 is this one, correct? So you have VCC, ground. Pin 14 is VCC, pin 7 is ground. Yeah, pin 1 and 2 is input, pin 3 is output. So you decided to use this one, this gate lah. There's 4 gates here, so we use one of the gate here. All right. So 7400. So you have here. This is a circuit diagram, or you can also call it construction diagram. Okay. So you have the input going to pin 1 and pin 2, output going to pin 3. This is the output. So when you change it, when you change the input, the output is reflected. So pin 7 is the ground, you connect it to the ground. Pin 14 is VCC, connect it to VCC. All right. This is how, this is the circuit diagram. This is a logic diagram, and this is a circuit or construction diagram. Okay, are you all clear now with the circuit diagram and the? Are you all clear with the logic diagram and the circuit diagram? You all clear? Yeah. You can actually download the digital works and play with it. It's free of charge. 20 years ago, we also still use it. 20 years ago, we used this before. Year 2000, we also use it in MMU. Okay, clear? So how you import the part number, you can go to part center. Then you can see from here, you got integrated circuit. You can see quad input to NOR gate. So you can put it here, and you can see the part number 7402. Then from there, 7402, you open your PDF file. You can see the gate 7402 looks like how this looks like. Pin 2 and 3 is the input, pin 1 is the output. Okay, this is how you should wire up. Okay, any questions so far? Okay, so you try to get all this chip, provide the input, okay, and test out the truth table. Okay, question number 2. Prove the NOR gate is equivalent to negative NAND gate by constructing. So, all right. So you want to prove the NOR gate is equivalent to negative AND gate. Right. So over here. So this is a NOR. This is a NAND gate. So where's the question? I'll do the second part first. Right. Prove that the NAND gate is NOR gate is equivalent to a negative AND gate. Okay. Okay. So I try a new thing okay. Try a new file. Okay. New circuit. Okay. So what is the? So we need to give a text. You want to. So how many points? Proof that NOR gates is equivalent to negative AND gate using okay. So you want to prove NOR gate is equals to negative AND gate. So let's do the input. So over here, where's the input? Input. Okay, and you have a NOR gate. NOR gate, and then the output. Okay, then you do the wiring. Attach, 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 attach. Okay, so this is a NOR gate. You want to prove that NOR gate is equivalent to negative AND gate. So negative AND gate, so you have to use an inverter. And okay, so wire attach. Okay, so then you see, change here. Okay, so it's proven. Now you have to use this, the chip. Okay, they say by constructing a NOR gate using 7404 and 7432. Okay, so we go to part center, put a hex inverter. Layout here 7404, and then you have two input AND gate, and here there's one 32 7408 AND gate lah, 7408. So you got to quad two input AND gate. Okay, all right. So first you give power VCC first, ground first, ground everything first, so nothing will get burned. Then you have VCC. Where is VCC? VCC. VCC. Okay. So connect. Okay. Then you have to refer to the PDF document. How does the chip lay out in the 7404 is input 1, output 2. Okay. Input 3, output 4. So you have two input. So put here the input 1 and input 2. Okay. So input 1 connect to 1. Input 2 connect to pin number 3. Okay. Then the output connect from here to here. Okay, 7408. So look at 7408. So pin 1 and pin 2 is the input. Pin 3 is the output. So then you put in the output in pin 3, connect the output. Okay, then you're done. Okay, then you're done. So this is the logic diagram, and this is the circuit or construction diagram. Okay, so it's proven using the truth table. Okay, clear? 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 Any questions so far? So far, any question? Okay. Any questions so far? You can Google digital works, then you can get from there. Okay. Is FOC. Yeah, handwritten lah. So you have the simulator, isn't it? So then the simulator can tell you just hand draw lah. If you do the lab, you must have the circuit ready. Okay, so it is important to have the circuit diagram ready. Okay, so once you have the circuit diagram, so when you go to the lab, you know which pin to wire to which pin. Then you can get the lab done very quickly. Okay, right? Right, the lab report guide is Eng Hu already posted the guide. So you just follow lah. 3, 4, and 5. So you do 3, 4, and 5. Okay. Or report you have to do the report you have to do 1, 2, 3, 4, and 5. All right. Report you have to do 1, 2, 3, 4. The digital works is for you to practice only. Okay. Okay. Now question number 3. Perform a NOR operation on decimal input and convert the input to 4-bit binary before performing the operation. Okay, and draw the timing diagram. Okay. Draw the timing diagram. So the NOR operation, you have a NOR is a not N in it. NOR is a not all. NOR is a not all in it. Okay, not all. So you have like this. Then you have Okay. So let me connect first. Okay. So this is a NOR gate, alright? Okay, this is a NOR gate. So this is a NOR gate side. So when it's 1, 0, 0, so this A, and this is B, this is C, and this is D. Okay? When it's 1, 0, 0, when it's 10, 10 is 1, 10 is 1, 0, 0, so it's 0. When it's 13, right? This is 13. 13. Okay, also 0. When it's 7, also 0. It's only become 1 when it's 0. So this is for question number 3. Okay, then you draw the timing diagram. So you draw the timing diagram. So you have to use a Word. Have to use the Word document. So insert table. So let's say 20. 20. So this A, B, and this X. So when it's so you blank, all blank. No border. So when it's 1, 1, 10, so 1, 10, so 10 will be, this one will be bottom. One will be bottom. Okay, this one will be top. Top. And this one will be hey, cannot. Try all again. Okay, insert table. Put here, and here. A, B, C, D, and this X. And over here, put here, all blank. No border. Okay. So here 1, 0, 1, 0. So the output is 0. 0, bottom. So when it's 1, top, top. Okay, then the next one is what? 13. 13. So 13 is 1, 1, 0, 1. Okay, so this one will be top, top. This one will also be top. Okay, this one will be bottom. Okay, and the answer will also be bottom. Apparently they did not copy the border. Okay, then you can draw the timing diagram. You can put here like this. Left border, then you have bottom, and here you have okay, so this is a timing diagram. Then you can do for the next one is what? 13, 7. So it's 0, 1, 1, 1. So the answer is also 0. So this one will be bottom. This one is bottom. Then you have left. Okay, this one is top. Top. This one is top. And also left. This one is top. Okay, so this is the timing diagram. Okay, this is a timing diagram. Okay, but you can use to draw it by hand. Okay, you can repeat it for AND and NOR gate. Okay, question number 5, you need Karnaugh map, so you cannot do yet. Okay, question number 5. Next week we tell. Okay. Right. Anything? Anything?
Sir,
Yes.
can I see the timing diagram?
See the timing diagram.
Need to see.
Can see it now? Can
Yeah.
Yeah.
As for the
Yes.
so
Question
the
number 5 you do next week
question number 5.
Karnaugh map is required for question number 5.
Oh.
Okay.
Okay. So about question number 2, how do we prove it?
How do you prove it? Using truth table? Truth table.
Truth.
1 to 4. You must submit 1 to 4. 1 to 4 submit. Okay. Okay, I stop the recording now. Then 12 December, that's the due date. I think no need for the moment because you need Karnaugh map. Yeah, stop the recording first.